So let me start on the topic of journeys, and I'll just talk quickly about my own journey, and then what the journey that we're taking together as a global community. My journey started in the early 80s, where I worked at a coal-fired power plant. I call this my hydrocarbon years. So it was a very dirty, hot, and sometimes dangerous environment to work in, but I learned a great deal. And in the mid 80s, I was recruited by NASA to work on combustion experiments that were flown on the shuttle and eventually the space station. And they all produced soot similar to this. This is actually decane fuel, which looks a very clear liquid in its form when you're looking at it. But when you burn it, you get these kinds of soot particles, and we'll talk a little bit more about that later. So through the mid 80s, that's the kind of work I was involved in. And then in 87, I changed into what was a field that was new to me, which was hydrogen, mostly liquid hydrogen, and got involved in a lot of research and development, technology development, systems development of liquid hydrogen systems. And here's a few pictures of various tests that I was involved in, and we published information on. The top was filling of liquid hydrogen tanks without having to vent, so you don't lose any hydrogen. And the bottom is sloshing of hydrogen and the thermodynamic response in a tank. And spoiler alert, it can be very exciting responses that you don't want, or it can be very controlled. And understanding those parameters was very important to us at the time, and it remains important, of course. These ground tests actually during this time frame were to inform flight tests and space exploration programs. But of course, they're useful now for a lot of the ground work, quote, groundwork and energy and mobile vehicles on the Earth. So I'm getting a lot of interest in some of this early work that I did in the 80s and 90s. But in terms of the continued development work that I was involved with hydrogen, that top right is actually, I think I did this in the late 80s or early 90s, was a headquarters requested, NASA headquarters requested study on splitting water, electrolyzing it, and then providing it to vehicles, space vehicles of various sorts, the hydrogen and oxygen, either on orbit or on the lunar surface or on a planetary surface. So it's interesting, other than the kind of old-timey graphics from the 80s and 90s here, the physics haven't changed. I mean, all of those systems that you see there and components and so forth are exactly still what you need to do this kind of splitting of water into hydrogen and oxygen streams. Hydrogen is what most people are interested in at this point. The bottom right one is the National Aerospace plane that I worked on. We did slush hydrogen research, both in terms of technology development and also systems demonstrations. And slush hydrogen is a mixture of solid and liquid hydrogen, and we had up to 50% solid fraction in many of those tests. So a lot of interesting stuff there. And of course, you can pack a lot more hydrogen in when you store it that way. In 96, I kind of made a bit of a shift or maybe an evolution in my career, going from looking at liquid hydrogen, and at the top right, I'm sorry, the top on the left-hand side, you see on the top what happens in a liquid hydrogen tank from a thermodynamic standpoint as it sits there in storage. So you get superheated vapor at the top, saturation near the interface, and then a liquid is subcooled as you get down towards the bottom, typically, as it sits there. Well, that changes in space. In space, you don't have gravitational effects, or it's a low gravity, microgravity environment. So the position of liquid and vapor changes. It's driven a lot more by surface tension, by accelerations in the vehicle and that sort of thing. So you have a totally different thermodynamics, not totally, but it's certainly very different. So that was a large part of the kinds of research and testing that I did, was looking at these kind of phenomena. But the evolution in my personal journey was to then start looking at how do you integrate these into launch vehicles, in other vehicles of various sorts. And of course, there's corollaries to this, to the kind of vehicles that are being looked at now with liquid hydrogen. And then in the bigger picture, how do you, integrate this into system architectures, whether in this case it's a space exploration system, or whether it's an export of liquid hydrogen by shipping, for example, or an energy storage of some type, where you've got an architecture where you store and distribute it where you need it. And then finally, what are the key interfaces, which are always come into play? One of the things I was responsible for in this time frame was the interface between the new crew exploration vehicles and other visiting vehicles that were coming to the space station, the requirements for that interface. So this was a very important period in my own personal development to understand this big picture, and it has informed and driven my perspective on things going forward. I always look at it from that architecture and then drill down into what solutions make the most sense for that particular system or system of systems the DoD likes to talk about. So in 2012, again, a bit of a shift, and this is more of an innovation and entrepreneurship. I was asked to take on a new role at NASA called the Sector Manager for Energy and Materials. The center I was working at, its core competency was in those areas, energy and materials, solar panels, autonomous and intelligent control of power systems, as you see in the space station, kind of demonstrating that at the top. Cryogenic fluid management, and then the delivery of those cryogenic fluids to engines, rocket nozzles, like you see further down. Tribology, materials, especially high temperature materials, a lot of that made its way into wind turbines and so forth. And then at the bottom, fuel cells, and we also did battery research. So my responsibility in that last 4 years that I was at NASA was to set up and negotiate license agreements with industry partners, trying to transfer that technology and that know-how out to the energy industry in particular, but other industries that were interested in it, as well as the materials. That borrowed heavily on my experiences that I did in my, quote, spare time on the evenings and weekends. NASA allowed me to start multiple companies as long as there wasn't a conflict of interest with my work at NASA. And that's what I did from the mid-90s through today. 5 of those startups I did up through 2016. And I'm showing the analysis and modeling side of it. There's lots of hardware stuff too I have on my website if you're interested in terms of how these systems actually got developed, built, and deployed. But what I found over this time frame was the ability to model and analyze these systems is critical. And it allows you to rapidly move through feasible trade spaces. And the term now digital twin is being used. At the time when I started doing this, I don't recall that term being around, but it's sort of a similar idea that you go through these trade spaces with these models, and then the model evolves along with the hardware ideally, so that it becomes a test bed, quote, digital test bed, where you can start to add in new capabilities or new technologies and see what the impact is on the overall system. So again, this was very informative for my own personal approach to things. And then from 2016, after I left NASA forward, I've been involved in a number of projects, mostly around liquid hydrogen, almost exclusively now, including the largest liquid hydrogen storage sewer that just got constructed and commissioned. I think it was commissioned within the last couple of years now, a year and a half or so, down at Kennedy Space Center, 50% larger than the one that was used for all the shuttle launches. And that's at the bottom right there. And I'll talk about that in future sessions. I was on the design team for that, and I was responsible for the zero boil-off system that we put in there that also could re-liquefy and condition the liquid hydrogen. And I'll have a lot more to say about that, because there's a great deal of misconceptions about the fact that you have unavoidable boil-off with liquid hydrogen systems, and that's just wrong. The advances in cryogenics, cryocoolers, and cryorefrigeration has gotten to the point now where you can eliminate the boil-off completely and actually re-liquefy. So with that, let me move on to our journey together, because all of that and on all of our personal journeys really in the big picture are irrelevant if they don't impact the journey we're trying to make together on this topic. And on the left-hand side is that view of where we are currently in our legacy fuels and what we've been doing since the Industrial Revolution started, and the vision of where we want to go. And this webinar series is going to focus on this. How do we transition with hydrogen, liquid hydrogen in particular, which is the focus of this webinar series, to a better future? And this is sort of the compass for this webinar series going forward. It's also equivalent to that that time when you get on a plane and the flight attendant tells you that what the destination is and tells you that if that's not your desired destination, you need to get off the plane. So this slide is sort of that for folks who look at this and don't like what they see. You're in the wrong place. You don't want to be here or in future sessions. On the other hand, if this is a journey that you'd like to take together as a global community and want to be involved in this, you're in the right place. So stay put, and I hope you continue to tune into these sessions. So I'm going to start off with 3 whys. Why is a very powerful question. Toddlers learn it very quickly to challenge the status quo. In their case, it's cookies before dinner or something of that nature. We're going to use it to challenge the status quo with legacy fossil fuels. So first of all, why transition away from fossil fuels? I think you'd have to be living under a rock for a long time to not understand the climate side of this and the changes. This is a great resource available to folks. I'd invite anybody to take a look at this. This is hard data. This is evidence. And you can look it up. You can see how it's changed over time. On the left-hand side here is all of the causes. Again, I think these are fairly well known, and we're living through almost all of these right now. In fact, all of them. We've already seen the impacts, and we are heading down this path at a very scary rate. This isn't really news by any stretch of the imagination. This is a fascinating, and by the way, these are all links that I have in these slides that I'll make available afterwards. Carl Sagan gave a congressional testimony in 1985 that basically described every bit of this and told all of us we were going to go there. Al Gore was actually one of the senators in this congressional hearing, and of course, years later, as vice president, he started to focus on this. But I would encourage you to listen to Carl Sagan the late Carl Sagan talk about this. It's fascinating. There's another part of this that I find very interesting, and I'll add it right now. Nobody seems to, there's some people hanging on to the idea that climate change isn't caused by this, but let's ignore that for a minute. No one argues with the bottom left-hand side of lists here that I'm aware of. These are all things we've come to accept with the use of fossil fuels, and the impacts are enormous on health, on livelihood, on the loss of life, on the loss of property, and casualty losses. These all come with fossil fuels, and we've kind of accepted them because we're used to them, but the impact is enormous. So that's the first why. Second why transition to hydrogen? Well, the short answer is to mitigate everything on the previous slide. So just to give you a recall from 1 second ago, that's everything on this slide. Everything is addressed immediately by the transition to hydrogen, or begins to improve it immediately and continues to improve it over time once we make that transition or begin making that transition. So that's the short answer. There's a few others here I'll just bring up quickly. Hydrogen is fascinating from the standpoint of it's an energy carrier, an energy storage method, and a fuel, all 3. That's very unusual in terms of solutions that we have to tackle this issue. It also does not have many of the drawbacks of the other solutions. Now, it has its own. All solutions have their pros and cons, but I'm mentioning here some of the things that are the Achilles heel of many other solutions that hydrogen simply isn't an issue for it. It's a very simple, straightforward solution in many regards, and these are some of them. And then a final aspect of using liquid hydrogen in general, including liquid hydrogen, that is often overlooked, and that's the ability to produce large quantities of potable water and from non-potable sources in many cases, including seawater. So there's a lot of synergies here where in regions where water scarcity is a problem or is becoming a bigger problem. And that's something that's unique to hydrogen. I'm not aware of any other solution that provides the ability to actually create large amounts of potable water. So something to keep in mind. So the third why. Okay, if you're convinced of hydrogen being at least a solution to have on the plate and being considered, why liquid hydrogen? This chart has a lot of information on it, but I'll just call your attention to the far right. Any of these solutions make sense for particular use cases, obviously. The question is, When does liquid hydrogen at cryogenic temperatures start to make sense? And that's going to be, as I said, the focus of this webinar series, and it's where my core competency is in my company project portfolio is focused in. So when you look at liquid hydrogen, it's low pressure and at a very low temperature as well, minus 250 degrees C or 20 degrees K. So of course, the low temperature is a challenge. The low pressure, however, is a benefit compared to some of the other options you see there, because you don't have to have large, very thick composite overwrap or other materials that can maintain the kind of pressures that you have in some of these other options. Excuse me, liquefaction is the main work input. I use the term work input. That's a thermodynamic cycle terminology, but think of it in terms of the electrical energy that you have to put into the system to get it into the storage mode that you're trying to do. And all of these systems have some amount of work input that they have to that you have to provide to store them in the way they need to be stored. The supply method, what I'm implying with that is, how do you get the hydrogen where you need it? So in the liquid hydrogen case, you can transport it, which has been the case for decades now, by barge or truck or train, and soon by ship. But you can also produce it on site at the point of use. This is a complete paradigm shift from fossil fuels, and a lot of folks and organizations, it takes some time to get their arms around this. You can do the entire process of generating hydrogen renewably from renewable energy sources, splitting it off, getting the gas, liquefying the gas, and fueling whatever system or whatever storage you're trying to do all in one place. And that's unique. The density of liquid hydrogen is almost double that of compressed gas, and quite a bit more than the other options in general. And then the mass fraction is very key, particularly when you're talking about mobile applications. So any kind of transportation, vehicles where you're trying to pack in as much fuel as possible while not having a lot of extra mass for the storage container it's within, liquid hydrogen can get you up to 80%, and that's defined as the amount of hydrogen fuel divided by the fuel plus the weight of the storage containment. And depending on what your application is, for example, the shuttle external tank was over 90 in the mid 90s or maybe even upper 90s mass fraction. So those kinds of numbers are possible. Again, I don't think there's I see a lot of quotes and a lot of talk of folks talking about mass fractions. And they keep quoting compressed gas and claiming it's true of all hydrogen storage, and it is not. Liquid hydrogen is much higher. So I came up with a mnemonic just for this webinar, and I liked it so much, I trademarked it. But it's 2020 vision for the countdown to hydrogen. Before I get into that, let me describe this graphic very quickly. This is from the Department of Energy, U.S. Department of Energy. It is gravimetric density across the horizontal axis. So that's the amount of energy in a unit mass of hydrogen. And then on the vertical axis is volumetric density. So that's the amount of energy in a particular unit of volume. So liter, whatever volume you want. So on top of this then are all the points for various fuels. What I'm calling the fantasy fuel in the top right corner doesn't exist, but that's why I'm calling it a fantasy fuel. That's where you would love to be. You'd love to have a very dense, both gravimetric and volumetric, energy dense fuel, but it doesn't exist. So you have to make some trades. The trades we've made for the last several decades are the legacy hydrocarbons that you see over kind of the top left there that have a high volumetric density, but a rather mediocre gravimetric density, gasoline, JP8, diesel, so forth. You can make the trade to have a little bit less volumetric density, excuse me, about the same gravimetric density if you go to propane or liquid methane. Liquefied natural gas, of course, is mostly liquid methane. So you can kind of think of that when you see the word methane. The problem, of course, there is that methane is a 25 times more powerful greenhouse gas than carbon dioxide. So even if it's cleaner, quote unquote, burning, any leakage or releases that you have in your system is having a huge impact on greenhouse gas emissions. So hydrogen, of course, gets rid of all of that, and you have a much higher gravimetric density, almost 3 times conventional fuels, but you can't pack as much in the same volume. So that's the trades. I mentioned, or I show a nuclear symbol up here. It's hard to put this on this kind of a plot because it's a very different fuel quote, if you use the word term fuel, and it has its own risks, of course, and trades. I'll be talking about that in the future session. There is a role potentially for nuclear to have in hydrogen, but we'll chat about that next time. So the 2020 vision for the countdown to hydrogen mnemonic. This is to help you think about some of the key facts for hydrogen. 20 meters per second is the rise rate of hydrogen in air. Yes, that is very fast. And by the way, that's the reason why hydrogen is safer than most legacy fuels in many applications, despite what many people's preconceived notions are. Again, in the safety session, we'll talk more about that. 20, the second 20 in 2020 vision is 20K. That's the temperature in Kelvin, which is equivalent to minus 253 C for liquid hydrogen. And then the countdown starts at 5. These are the 5 safety tips that you kind of keep topmost in your mind with hydrogen. The first 3 are with any hydrogen: ventilation, leaks, and ignition sources. The last 2 are specifically for liquid hydrogen. Cryogenics, you got to make sure you have precautions that you're working at very cold temperatures, and phase change from liquid to gas, and in some cases the other direction, that you have to have in mind with operations and design of your systems. 4 on the countdown is the volume of hydrogen needed to match the energy content of common liquid fuels, but don't forget efficiency. If you're using a fuel cell that's 2 or 3 times more efficient than your combustion process, then now you are starting to eat away at that differential in the amount of volume that's required of hydrogen. 3 times is the energy content mass of hydrogen compared to the other fuels. So for the same kilogram of hydrogen, getting close to 3 times the energy as the legacy fuels we use. There's 2 spin states of hydrogen, ortho and para, which becomes very important when you start talking about liquid hydrogen at cryogenic temperatures. Again, a topic for future. 1 proton per atom, which most folks know, and then of course 2 atoms per molecule of hydrogen, and that's why you see H2 used, or LH2. That's what the 2 stands for. And then finally, 0 is the amount of carbon emissions. And as we talked about before, no smoke, no soot, no particles, no environmental impact. And that's another topic we'll talk about in myth busting. There's been some information about that later. So I'll end this part of this session in particular with this final slide. When I finished my career at NASA and started my 6th company, this was our vision. The nexus between energy, water, and food that could be addressed by hydrogen anywhere in the world with renewable energy 24 hours a day and 365 days a year. So this is my call to action. If you want to consider it that, let's build a better future together with hydrogen. And with that, I'm going to do just a quick look at what sessions are coming up, sort of to whet your appetite. Future sessions, we're going to talk about history, evolution, and testing. If you did the pre-test that I had out before this webinar, you know that hydrogen was the first fuel used to develop jet engines in the 1930s. It was successfully flown. Liquid hydrogen aircraft engine was flown in the 1950s. A liquid hydrogen engine with afterburner was developed and ground tested successfully also in the 1950s. And then in the early 1960s, it made the jump to the space industry, and aviation and aeronautics kind of got amnesia for multiple decades about the benefits of hydrogen, where the space industry built out all of the necessary technology and systems basically for large-scale use of liquid hydrogen. So we'll talk about that. Another future session will be on basic safety. This seems to be a very important and interesting topic of interest to many folks. So we'll go through that, how to design and operate liquid hydrogen systems properly. Modeling, analysis, and development, as I mentioned, very important to understand what's out there, how to do it, how it impacts and informs your system as you develop it and deploy it and operate it. And then some future advancements. I mentioned cryo-refrigeration, cryocoolers. We'll talk about that. New material advances, composites, thermoplastics that are beginning to be tested and have been tested in the past, actually. There's been quite a bit of testing, particularly composites, that we'll talk about. And then new engineering tools. And one of the things my company's doing is putting out open source tools available through GitHub and trying to build that up into open source, globally accessible tools that folks can use to begin working with liquid hydrogen systems. And then finally, and I'm not sure where this will hit in our sessions in terms of timing, but this is, I think, critically important, is what's the strategy and implementation approach? And this is a methodology I've developed over the years and apply to all my projects now, and how you plan, develop, and launch rapidly, but also making sure that you're very comprehensive in your approach.